Hi, I'm Mr. Franz, and we're going to go over the answers to the Acids and Base Review worksheet. The first 7 questions are true, false. Number 1, acids turn litmus paper red. That's true. Number 2, bases turn litmus paper red. Well, if acids do it, then bases must do something else, so that's false. Bases actually turn litmus paper what color? The answer is blue. Acids have a pH of less than 7. That's true. Bases have a pH more than 7. Also true. Bases feel slippery and give more hydroxide ions. That's true. Acids would have hydrogen ions, H+. And number 6, acids taste bitter. That's false. What do acids taste like? Acids taste sour. Number 7, calculate the pH and pOH for a solution with a hydrogen ion concentration of 2.3 times 10 to the negative 2 molar. So we're going to look at our pH square, and you'll see on your pH square that if we want to go from hydrogen ion concentration, we go straight up to pOH, to pH rather. So we need this equation. pH is equal to the log of the hydrogen ion concentration. Substitute in our 2.3 times 10 to the negative 2 molar, close the parentheses and hit the equal sign or the enter button, and you get 1.64. If you get negative 1.64, that's okay. You just forgot to take the negative of the log. I often omit that on purpose because I can switch from a positive to a negative and back in my head. So just remember to flip the sign to from a negative back to a positive. Now that we have the pH, it's a simple matter to find the pOH. We just have to remember that, oh, by the way, this is an acidic solution. pH is less than 7. We just have to remember that the pH plus the pOH is equal to 14. We can rearrange it to say that the pOH is equal to 14 minus the pH. Substitute in our 1.64 for our pH, and our pH our pOH is 12.36. Number 8, calculate the pH and the pOH for a solution with a hydroxide ion concentration of 7.3 times 10 to the negative 11. Well, if the hydroxide ion concentration is what we're looking at, that's this right here, then we're going to have to go for the pOH first. So pOH is the negative of the log of the hydroxide ion concentration, just like the other one, but we're talking about hydroxide ions instead of hydrogen ions. Substitute in our given, and very quickly we come up with 10.14 for our pOH. Now remember, the pOH scale is the opposite, it's backwards, so a small number on the pOH scale is basic, which means a large number is acidic. It's backwards from pH, don't forget. Now we just do the same thing we did before. pH plus pOH is equal to 14. So pH is equal to 14 minus the number we just got. Plug that in, and we get 3.86. Number 9, calculate the hydrogen ion concentration with a hydroxide ion concentration equal to 9.3 times 10 to the negative 10. So look at our pH square, and you'll notice at the bottom there is an arrow that goes back and forth, and it says that the hydrogen ion concentration times the hydroxide ion concentration is equal to 1 times 10 to the negative 14. This should be a superscript here, but these two multiplied by each other are equal to 1 times 10 to the negative 14. We're going to rearrange it to get H. Anytime we take this equation up here and rearrange it, 1 times 10 to the negative 14 divided by one of them is going to be equal to the other one. Pretty simple. All we have to do is substitute. Our given goes down on the bottom, down here, and solve it, and we get a concentration of 1.08 times 10 to the negative 5 molar for the hydrogen ion concentration. There should be a capital M after that, moles per liter of hydrogen ion. Number 10, calculate the OH concentration for a solution with a pH of 3.21. So we're starting at the upper left-hand corner of our pH square, and we're going to the bottom right. Now, it doesn't matter which direction that you go. You can go across the top and then down, or you can go down and then across the bottom. I'm going to go across the top on the pH square and then go down to the hydroxide ion concentration. I think that this is much easier to do the pH plus POH equals 14. Rearrange it. POH is equal to 14 minus pH, and subtract the 3.21, and we get a POH of 10.79. Now we're going to go across the bottom, we're going to go straight down. Going straight down, we're going to use this equation. The hydroxide ion concentration is equal to 10 to the power of the POH. So we're going to take our number that we got over here, and we're going to move it and plug it into a superscript right here. Now, if you want to use that little caret thing, that little thing that goes up like that and down, the little up arrow pointing thing, you can use that on the TI calculators, and it works just fine. I don't like using that when we're talking about exponents, but in this case, it works really well. Just don't forget to use the sign change for this little negative sign. Don't use the minus button. Use the little sign change in parentheses next to the decimal point for the negative. When we substitute, we have 10 raised to the 10.79, which gives us a hydroxide ion concentration of 1.6 times 10 to the negative 11 molar of hydroxide. Now we're going to write some proper names and formulas and determine if the solution is acidic or basic. The first one, KOH, we should know from our ionic naming rules that we just name the metal and then name the polyatomic ion. So the metal here, K, is potassium, and the polyatomic ion is hydroxide, since our metal doesn't have any Roman numerals associated with it. So potassium hydroxide. Now for our acid naming rules, H2SO3. SO3 is a polyatomic ion. I know that because there are more than two elements. There's an H, there's an S, there's an O. So it has more than two elements. So it's not a binary compound. It must be a ternary compound or a compound with a polyatomic ion. And the polyatomic ion is, of course, this SO3 right here. So I look up SO3 on my table, and I find that its name is sulfite, S-U-L-F-I-T-E. And anything that ends in ITE, remember, ATE becomes IC, ITE becomes OUS. So this would be sulfus, I guess. Remember, sulfur and phosphorus are a little bit of exceptions. We add the extra syllable. So sulfus becomes sulfurous, and we get sulfurous acid. Number 13, magnesium hydroxide. Well, when we're doing formulas, we write first the symbol for the metal and then the symbol for the polyatomic ion, and then we crisscross the charges. Magnesium has a charge of +2, and the hydroxide has a charge of -1. So +2 here, and this is -1. So when we crisscross, our 2 comes down here, and we end up with an OH in parentheses 2 for magnesium hydroxide. Number 14, nitrous acid. So we have an OUS ending here. So that means that it must have been ITE in our polyatomic ion list. So NITR and then ITE, so that's nitrite, which is NO2. NO2 has a charge of -1. So to be an acid, there would be 1 H. So HNO2 is nitrous acid. Number 15, H2S. Now this has other names in other naming, with other naming rules, like hydrogen sulfide. But when we name it with acid naming rules, we have to look and see that it is binary. There are only 2 elements here, hydrogen and sulfur. And so for binary acids, we start with the prefix hydro, and then we just append the name of the non-metal here at the end, The nonmetal is sulfur, and we change it to IC, the ending to IC. This becomes sulfuric. Normally it would be sulfic if it followed the rules, but it's an exception. We have to add the other syllable, so it becomes sulfuric. We put the hydro in to indicate that it's binary, and we end up with hydrosulfuric acid. This shouldn't be confused with sulfuric acid. That would be H2SO4 with the polyatomic ion. H2S is hydrosulfuric acid. Now let's go down and just figure out which ones of these are acids or bases. Well, clearly all the ones with the name acid are acids, but let's do it more systematically. First, we'll look at KOH. It ends in OH, so it's a base. H2SO3, sulfurous acid, starts with an H, so it's an acid. MgOH2 ends with a hydroxide, so it's a base. HNO2 starts with an H, so it's an acid. And H2S starts with an H, so it's also an acid. Anything that starts with an H is going to be an acid. Anything that ends in an OH is going to be a base. In number 16, you're asked to balance this reaction and then label the acid, base, salt, and water. So first off, to balance this equation, if we look, we'll see that we have two H's and we have two OH's. So our two H's and our two OH's are going to make HOH, which is water, but how many are they going to make? Well, they're going to make two of them. So HOH over here, remember, is also known as water. We have two things that are left over. We have an SO4 and we have an Mg. Mg is our metal. It's +2. And I know that not just because it's in the second column of the periodic table, but because there are two hydroxides here, and each hydroxide is -1. So if there are two hydroxides, then the metal here must be +2. And I know that sulfate, SO4, is -2 because there are two hydrogens. So I know that these are going to be balancing with each other. We're going to put the metal in front, Mg, and then the polyatomic ion at the end, SO4. The acid, this is the acid. I didn't label them on the PowerPoint, but this is the acid and this is the base. It says label the water. Well, the HOH or H2O, this is the water. And this right here, magnesium sulfate, is the base. The next problem, HBr and CaOH2. So the HBr is the acid. I know that because it starts with H. And the CaOH2 there is the base because it ends in OH. So the first thing I want to do is I'm going to take the H's here and the OH's and make some water. The problem is there's one H and there's two OH's. So I need to fix that problem. And I can do that by putting a 2 in right here. Now I have two H's and two OH's, which means when I make my HOH, I can make two of them. Remember that HOH is H2O, of course. And now we need to do something with our calcium and our bromine. Well, the calcium there, it's +2. I know that because there are two of these guys, two of the OH's. Bromine is -1 because there's only one hydrogen. So my Ca has a charge of +2 and the Br has a charge of -1. I need to do my little crisscross, and that's going to make a 2 come up there. So CaBr2 calcium bromide is my salt. So going from left to right, I've got my acid, my base, two waters right here, and the salt calcium bromide. Here we have iron 3 hydroxide and nitric acid. The iron 3 hydroxide is our base because it has OH, and our nitric acid is our acid, well, because it's called nitric acid, but also because it has an H in the front. So I want to take this H in the front and mix it with these OH's and make some water. The problem is I've only got one of these, one H, and I've got 3 hydroxides. And and I need to have the same number. So I'm going to need to have 3 of these nitric acids in order to correctly balance this equation. So now I have 3 H's and 3 OH's. So when I make my HOH, I can make 3 of them. Now I need to do something with my leftovers. I've got some leftover iron over here and some leftover nitrate. So let's write them down. There's my iron and there's my nitrate. Now my iron here, it has a charge of +3. And I know that because I have 3 hydroxides. So I know it's +3. My nitrate is -1, and I know that because there's only 1 H. So if this guy right here is +3 and this guy's -1, I need to crisscross. So I'd take my 1 and put it down there if I wrote 1s, and my 3 needs to go down here next to this other 3. But I can't put 2 numbers like that next to each other without parentheses. So I end up with FeNO3 3. That's iron 3 nitrate. So iron 3 hydroxide is my base. Nitric acid is my acid. Water is one of the products, and iron 3 nitrate is my other product. In this picture, you see a strong and weak acid dissolved in water, and you're asked to determine which one is which and explain why. Well, let's take a look. This HCl right here, when we put it into the water, you'll notice that there are no more HCl's. There are only H's and Cl's. So the process of going from HCl to H's and Cl's is called dissociation. And the HCl has completely dissociated. So there is no HCl left. It's all just H and Cl. And when we have complete dissociation, that is a strong acid. Now over here we have carbonic acid, H2CO3. Carbonic because CO3 is carbonate, and 8 becomes ic. So this is carbonic acid. And when we put it into water, we notice that, well, there's an H and an HCO3, and there's an H and an HCO3. So some of it has dissociated, just like the hydrochloric acid. But here's H2CO3, 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 H2CO3 over and over again. These guys have not split apart. And the splitting apart, the dissociation, is what makes this, what makes HCl on the other side a strong acid. And the fact that it does not split is what makes this a weak acid. So not dissociating completely, not dissociating 100% of the time, is what makes this carbonic acid a weak acid. Here's what I wrote. I said that the HCl is the strong acid because it completely dissociated into H and Cl. The other acid partly dissociates into H and HCO3, but 2/3 of it stays together. H2CO3 is therefore a weak acid. In number 20, it says, during a previous class we used litmus paper, phenolphthalein, and universal indicator to test the pH of different substances. Explain how these indicators work. Well, I'm not going to get into a detailed explanation of ions and things. That's really unnecessary in this class. Instead, we're just going to look at the colors they change, which you should already know. Litmus paper is used to determine whether things are acidic or basic. Litmus turns red in an acid and turns blue in a base. We always test with both colors because neutral won't change the color. And so water would just be wet litmus paper. And so we need to use both. And if one of them changes color, we know it's an acid or a base. And if both stay the same, then it's neutral. Phenolphthalein turns pink in a base, and it's completely clear in an acid. So when we put some in an acidic solution, it doesn't change the color at all. Only when it turns basic does it turn blue, or turn pink rather, and we use that in our titration lab in order to indicate an endpoint. Universal indicator changes across the whole colors of the rainbow. Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, and it's useful across almost the entire pH range it's best if you have a color chart that you can look up the pH with that color chart. All acid-base indicators work by changing color at specific pH ranges, and that's because they reversibly react with the hydrogen ions or the hydroxide ions in the solution. Again, not that important in this class how they work, but just thought I'd point that out. The last two questions involve identifying the Bronsted acid and Bronsted base, conjugate acid and conjugate base. The way we identify the Bronsted acid, remember that the Bronsted acid is a proton donor, meaning a hydrogen donor, and the Bronsted base is a proton acceptor, meaning it's the one that takes the hydrogen. So if we look at our equation right here, we see two compounds, NH3, which is has the common name of ammonia, and H2O, which common name is water. And we're going to react that, and we're going to form this NH4 ion, ammonium, and hydroxide ions. So which one of these two compounds at the beginning is going to donate an H in order to look like something at the end? Well, it's going to be the water. The water donates the H. So in this case, by the Bronsted-Lowry definition, the Bronsted acid is the water, and the ammonia is the Bronsted base. Now, if we follow that magic hydrogen to the product side, who has it right now? Well, that's the NH4, the ammonium ion. That has become the conjugate acid in the product side, and the OH ion is the conjugate base. The last question, HNO2 plus H2O yields H3O plus NO2 minus. So NO2, that's nitrous acid plus water, yields the hydronium ion plus the nitrite ion. So we want the reactant side to look like the product side. Which one of these two is going to donate a hydrogen so that the reactants look like the products? Well, the nitrous acid is going to donate, and so since it donates a hydrogen, it's known as a proton donor in the Bronsted-Lowry theory. So since it's a proton donor, it's the Bronsted acid. The water accepts that proton, so it's now the Bronsted base. Remember, in the previous equation, the water was the acid. So in this equation, the water is the Bronsted base. The conjugate acid is the one that's got the H now, so that would be the hydronium ion, H3O plus. And the nitrite ion from the nitrous acid is the conjugate base. Hope you got all these correct. You can always go back and pause at any point if you need to review this, and you should be able to find the full review sheet on my website.